This is our final day on section 3.1. We're going to deal with a new definition for the derivative, and again, derivative really is a fancy name for slope. We're going to work on getting that slope at a particular point called x, and what we're going to do is we're going to start with the average rate, just like we did in the first part of 3.1, but I'm going to give it in a little bit different form. This one is kind of hard to see, but it's basically the same as this one without the limit. The slope of the secant line, that's the average rate, is connecting the value that I want to find the slope at to some other point on the graph. So all these lines represent points on the function, and if I find the slope at those points, I get an approximation for the slope here at x. And you can see as we move down along the curve, getting closer and closer and closer to the x. As you check out these slopes, they are positive, but they're kind of shrinking down and decreasing in value. And look at, as we get really close, the approximation for the secant line is a really good approximator for the tangent line right here at x, f of x. So this, for your note purposes, is f of the second point. So that's kind of like saying y2 minus the y1. It's just a little function notation instead of saying that, which they are all marked here, over x plus h. This means I have a point a little bit past x minus the original. And that's how we get the slope of the secant line. But then eventually, if you take the limit as h goes to 0, you shrink the distance you are away from the original point. Shrink that down to 0, and then what happens is it turns into the slope of the tangent line, which is what we call the derivative at x. So this is saying f's slope at x, f's derivative at x. Some people refer to it as f prime of x. It all means the same thing. It's instantaneous rate of change. Over here, I put our formula from the first part of 3.1 that we've already tackled. So this is the limit definition we first experimented with to find the slope at a particular a value. Well, what happens is this new definition is just a slight twist. Instead of saying function value minus function value at the desired point over x minus a, I'm going to say f, but a little bit further away, so that's why we say x plus h, minus the originating height of the function, all over the difference between our 2 points, which really is just this h amount. And then as we see in the picture, as this h amount is shrinking, this is the h down here, this is how far I am away, as it shrinks, these 2 points merge and become 1 point, and so then we get the slope, instantaneous rate of x. This portion without the limit has a special name. We call it the difference quotient. Okay, so if I refer to something as the difference quotient, I'm talking about the insides of the limit. How does this apply? We're going to take a function f of x that you know from your past, because it's easy to identify the slope on a linear function, and it'll show you the technique works. So right now, I would say, what's the slope of this line? And hopefully you're all going to tell me it's 3. So in part A, we're going to find the slope of the graph of f at a general x value x naught. So that x naught, again like before, treat it as a. It's just another value. It's a particular value of x. How our new formula works, and notation is key, you start with the limit as h approaches 0 of, and then you take your x plus h, because that's our input. Here's our input into the function first. I plug it into function f. So x plus h is going into that x spot. Then I bring down the minus 4. minus this piece right here is minus f of x. Well, there's my f of x, all over h. Algebraically, I am still manipulating. The limit notation has to stay in the front. I have 3x plus 3h minus 4, and then distributing the negative sign. So now look at these like terms here that are canceling. Like terms canceling. I'm left with just the 3h over h. Still have the limit notation in front because h still exists. The moment the h's cancel out and you have your answer, that means this notation drops. Well, what is this? This is the slope of the line, which we already predicted. In terms of calculus notation, then, I would say f's slope, f's derivative, f prime, f's instantaneous rate of change at x is always equal to 3. Okay? Again, lots of words to represent slope at a moment. Now in part B, our job is to find the slope at a specified value for x naught. Our value is 5, so I want to find the slope at 5. How that works is the limit as h approaches 0, and now instead of inputting x plus h, we input 5 plus h into the formula. Minus 4 is a constant, stays. Minus, now this is the f of x, with x being replaced with 5. When I distribute and perform the order of operations, this is the line I get. Then I simplify all the constants. I'm left with, again, 3h over h. It divides out to get 3. What does that mean? It means specifically at the value of 5, I have a slope of 3. So I'm going to say f prime of 5 equals 3. Because this is a line, these are matching. Because everywhere on a line you would have a slope of 3. So if I'm asking about 5, I would have a slope of 3 still. And yes, you have to do out the limit definitions. The next example is a quadratic right here. So the first thing I would do is do the generalized formula for slope. And how we find it is we input x plus h into x. And this one has double expressions in terms of x. So I have to replace both of them with x plus h. So x plus h is going in for this x, then being squared, minus 2 times the input is x plus h. I have a constant at the end, I keep it, minus f of x all over h. Now, from here on out, we're algebraically manipulating. I bring down the limit notation, remembering your foiling skills. That's the first one, the binomial squared. Minus 2x minus 2h plus 1 minus x squared plus 2x minus 1 all over that h. And again, the desired goal is to cancel out that h. Well, let's see what we have. X squared here and x squared here cancel each other. Negative 2x and 2x cancel each other. 1 take away 1 cancels. I am left with 2xh plus h squared and then minus 2h for terms. Notice they all have h in them. So I am going to say h times 2x plus h minus 2 is being divided by h. This allows me to cancel the h. Once I cancel, I'm dropping this and I'm saying f's slope at all values of x is found by this formula that I'm about to create. I have 2x, because the h is going to 0, that gets wiped out, minus 2. So this is my slope formula for any particular x. Now in part B, we are going to not perform this operation all over again. We are just going to use our slope formula. So I'm going to say f prime at the given x naught, which is 3. So I'm going to say f slope at 3 would be 2 times 3 minus 2 using my generalized slope formula. So we're saying the slope at 3 should be a slope of 4. Grab your ruler, go to the graph, put a point at 3, wherever we're hitting, and then draw yourself a tangent line. So again, you squeak that ruler over and over, kind of balancing and trying to model the rate at which the function is increasing right at that moment. Once you think you have it, you draw yourself a tangent line, and hopefully your slope is about 3-ish. 1, 2, 3 over 1. Well, it's not quite 3 because this is not all the way up. So if we do it, 1, 2, 3 over 1. There we go. That's looking about 3-ish. Or sorry, 4-ish. I'm saying 3 because I'm at 3, but the slope is 4. And it's pretty close to 4. And that's what we care about. If you had a slope of 10 and you got 3 or 4, that would be a little off. But 3 and 4 are pretty close. I go to the next graph. The limit as h goes to 0 of, and I would try pausing the video and inputting yourself what we have. I have 2 times square root of x plus h minus f at x, which is 2 square roots of x, all over h. For this one, again, the goal is to cancel out an h. So I have to remember skills from my past to help me out with that. One thing I would do is I would notice these both have 2, so I would probably take out that 2 first and then analyze what I have left in my goal, again, of trying to get an h out here as a factor. The only thing we can do now is a technique from our past called multiplying by the conjugate. And we did this in the last section, so we're applying it again here. When I multiply by the conjugate, I still have h's. I'm bringing down my limit notation. I'm going to keep my 2 out in front, and when I multiply the conjugates, I get x plus h minus x. And then for the denominator, I don't distribute this through because, again, the goal is to cancel that h. So you don't want to mess with the h you're trying to get rid of because that's the division by 0. What happens now is when you simplify the numerator, you're left with 2h over that h times the conjugate. Now they cancel, so at this point I'm ready to say f's derivative at any x value. I have found my slope formula. What do we have? I have 2 over, h is going to 0, so that's a root x plus a root x. When I add those together, I have 2 over 2 root x, and then the 2's will cancel, so my slope formula is 1 over root x. For part B, we're finding the slope specifically at the x naught value, which in our case is 9. So I'm going to plug 9 into my slope formula, and I get 1 over the square root of 9, which is 1/3. So as I go up to the graph, when I go to 9, 5, 6, 7, 8, 9, I put my point, and then that's the slope I want to model, the slope right at 9. So if you take your ruler, and I'm running out of room on my desk here. Alright, I'm trying to model that slope right about there to get something that is just touching the curve, grazing it at that one moment. And then if I look at my slope, right here I'm connecting, down 1, 1, 2, it's a little bit more than 3, but that's okay. We're close to a 1/3 slope, and that's what matters most, is being close to that 1/3 slope. Next page, I would pause the video and try to do this one on your own, and then hit play. Part A, we're going to find the limit as h goes to 0 of 1 over x plus h being squared minus 1 over x squared, all divided by h. Simplifying with fractions means I want to create a common denominator. So my common denominator is going to be the product of these two. This is like a 3, and this is like a 4 or a 5. These are different bases being squared. So if it was 3 and 4, you would say the common denominator is 12. So I'm going to say the common denominator is x squared times x plus h squared. Kind of modeling it after my 3 and 4 situation to say it's the product of the two bases. Well, what happens in the numerator to make them equivalent, I multiply this one by x squared, I multiply this one by x plus h squared. And instead of dividing by h, I'm going to remember that I can multiply by h's reciprocal. So I don't have to work with that complex fraction anymore. Then the limit as h goes to 0 of, and I'm going to put everything together, x squared, x plus h squared. I have this x squared at the start, minus, and if it helps you, expand this out first and then subtract all the terms. So I have minus x squared minus 2xh minus h squared. All of that times our 1 over h. And again, this is the h going to 0, so ideally I want to cancel it. So the limit as h goes to 0 of, like terms are gone. Now look at what we have left. They both have h's in them. So what I'm going to do is I'm going to take out an h and a negative at the same time, make life easier. I'm left with a 2x minus h when I take that out over my common denominator that we had previously, times 1 over h. This is now gone. Cancel that out. And what am I left with? I'm left with, as h goes to 0, this is gone, so I can say f slope at any x value is found by, and we take what's left. I have a negative sign. This h goes to 0. That means that's a 2x over x squared, first factor in the denominator, times, let that go to 0, that's another x squared. In total, I have negative 2x over x to the 4th, which is negative 2 over x to the 3rd. That's my slope formula. So in part B, f's slope at the given value, which in this case is 1, is found by taking negative 2, dividing it by 1 cubed, or just negative 2. If I again go to the graph, let's check it out. We go to 1, and there I am at 1. And if I kind of zoom in on modeling that slope right at that moment, I think I'm just going to graze the corner here. I'm looking to have a slope of about negative 2-ish. So if I look here, down 2 over 1, pretty much almost on negative 2. So there's my match for my slope at 1. This next section, there's a certain pattern that exists for derivatives. And what we want to do is we want to discover the pattern so I don't have to keep doing this over and over again. There must be a nice shorter way to do it, and there is. So to discover the pattern, I want you to look at everything we've done so far. We started with the linear function. There's its slope. We did a square root function, but to help you focus on the pattern, I want you to focus on going from here to here. Okay? And then we did a quadratic. Here's its derivative. And the last one, I want you to focus on going from here to here. Take a few minutes, really process what you think the pattern is for these functions. And then what happens is the derivative for any x can be found by using this pattern we're about to create. So take this, a is your coefficient, b is your power, and design something that would be a rule based on what you're discovering up here. Pause the video. Okay, you're back. Hopefully you came up with a, the coefficient in front, gets multiplied by the power of b. Then I have x, but now it's 1 degree less, so I say b to the x minus 1. This is what we call the power rule for derivatives. And then, how do we use it? Well, we're going to be using it in application problems and any problems there and out. But when you go to do the homework, for the homework, the sections that look like these, you're going to do them out the long way to get practice with the long way. When you get to the applications, you can use shortcut methods, but let's figure out when we need it. So for this one, how high does the space shuttle go in 10 seconds? That's a pre-calc question. The height is going into the position function. S right here is representing the position because it's talking about the height. So I want to find S at 10. So that's going to be 9 times 1,000 plus 5 times 10. So that's going to get me a total of 9,050. And in terms of units, it's t seconds. It doesn't say units, so I will not label it if it's not given. The average velocity, this is like what we were doing before, average rate of change. But it's saying during the first 10 seconds. If it's during the first, then that means at time 0, that's an end point. So 0 goes with, plug that 0 in, you get 0. I'm creating 2 points because an average velocity and average rate of change requires finding the slope between 2 points. And then I'm going to take my next 2, which is the ending value of 10. So average velocity is going to equal 9,050 minus 0 over 10 minus 0, or 905 units per second, whatever those units are. This one, find the average velocity during its first 15,612 feet of its flight. During the first means we're starting at 0, 0, but now here's the glitch on this one. We have an ending height of 15,612 feet, but we don't know its time. So you grab your graphing calculator, and what you do is you plug in to y equals the position function, 9x to the third plus 5x. Now if we do a zoom 6, that's a standard viewing window. The problem with the standard viewing window is it won't let me get to my height here that I need. I need to know, well, what's the time to get to that amount? So I'm going to adjust my window, and I'm going to make sure I can see that. So that would be in the y maximum. I want to get that high up. So I am going to say 15,700, and then I'm going to change my scale because that's quite a jump, and I don't want to have really smushed tick marks all close together. So we're going to go by 1,000 at a time, and let's hit graph. And there you can see a portion of that cubic function. Well, what do we care about? We care about the 15,612, so I might have to adjust my window a little. So I'm going to say 15,612 is the target y value. Let's see where that is in comparison to my function. That's way up here at the top. So I'm going to adjust my window so I go over more and I can see this top a little. So I'm going to say x maximum. Let's change that. Let's make a jump to 50 and go by 5s. And then I'm going to go down here and I'm going to say 16,000, just so it's not so close to the top. So there's a cubic. And there's my line. And it's right up at the top. Let's try it. Second trace gets you the calculate menu, and we want the intersection feature, which is number 5. So the first curve, it is on the quadratic, and I want to make sure I am up close to that 15,000. So I'm watching my y values here until I'm close to that 15,000. Then I hit enter. second curve. Now it's on the linear function, so you can see the cursor flashing here. I'm going to just move it so it's closer to that intersection point. And then I'm going to hit enter. And then I'm just going to hit enter because I'm pretty close. And it's saying at that height it takes 12 seconds. So I'm going to go over here and put in 12. And then the average velocity is going to be 15,612 divided by 12. 15,612 divided by 12 gets me 1301 units of feet, because this one's feet, per second would be our slope. So that's the average rate. Now here's where the power rule is going to come into play. Instantaneous velocity means slope at a moment. It's kind of like before when we were finding the f of x at a particular number. So my position function is 9t to the third plus 5t. Now for those who have had physics, there's a connection. The rate at which position is changing over time is called the velocity. So to create my velocity function, which is really the rate of change of the position, then what I can do now is apply that new shortcut rule called the power rule, because I am finding instantaneous rate. How does it work? You take the 3, bring it down, that's the b, multiply it by the a. So 9 gets multiplied by 3, t to the, and then you decrease your power by 1. 3 minus 1 is 2, plus 5 times 1, because that's technically a 1, and then it would be t to the 1 minus 1 gives me t to the 0. So my velocity at any t is 27t to the second plus 5, because t to the 0 is a 1. At 10 seconds, v at 10, I have 27 times 100 plus 5, which is going to get me 2705 for my ending instantaneous rate, and then we'll just say it's feet per second matching the others. And that's it.